All right, one more example, a kind of surprising example where asynchronous clocks change our prediction or understanding of what would happen in a fairly simple situation. And what I have in mind here is to consider the motion of a bicycle wheel, right? So normally what you would think, based upon what we have discussed so far, is, if a bicycle wheel is rushing by, you would think that it would be Lorentz contracted. So it would be squashed along the direction it's moving. It would not have any of its height change, so the circle would kind of turn into an oval, turn into an egg. But it turns out that that is not the full story, because if you think about it, the bicycle wheel itself is an object where you can imagine that there are clocks on it, right? It has a reference frame associated with it, so it can have clocks on it. And again, if you have the bicycle wheel rushing by, you know that the clocks in front are going to be behind those in the rear. They always lag behind. Now, what that will mean is very interesting when you consider the motion of the spokes. So let me draw a little picture so that we can see what I'm referring to. And let me use a little piece of graph paper to try to keep this reasonably close to the shapes that I'm talking about. So imagine that we have a bicycle wheel. It's not a bad circle, I guess, right there. And let me draw some spokes on this. And I don't know what color. Let me choose green spokes for the heck of it. So imagine, in fact, let me just draw one spoke to be simple about it. So that's a spoke which at a given moment in time is vertical, right? Now this wheel is rolling. Now what will that mean? So let's look at the spokes a little while later, and I'm going to contract this up a little bit because it's assumed to be moving to the right with some speed, but I'm really interested more in what's happening with the spokes right now. And notice the following. So if you consider the fact that from the perspective of those who are moving with the bicycle, right, they would claim that as the wheel turns, the spoke that we see over there will go from the vertical position to, say, the horizontal position. And what we mean by that is that at one moment in time, let's say, for argument's sake, that at 12 noon, the spoke has now turned from its initial position into the position that we now see. So it's rolling along in that direction. Now, 12 noon, right, from the perspective of those who are moving with the wheel. So 12 noon, 12 noon. From our perspective, as we're watching this go by, what do we say? Well, we say that the clocks that are in the front are lagging behind. So that means that the spoke reaches 12 noon here first, but the clock over here has not reached 12 noon yet. It's behind, which means that the spoke must not yet have made the full turn. So from our perspective, what that means is, so I'll draw a rough picture here, and I'll show you more precise ones in a moment. So if I draw the shape of that spoke, then it'll look something like that. It will look bent to us because this guy over here has not yet reached 12 noon from our perspective. It'll take a little while longer. This guy will have to rotate down. That will take a little bit of time. This guy will rotate up in that amount of time. So we will never see straight spokes going from one side of the wheel to another. So let me show you a more precise picture illustrating that idea. So let's look at a bicycle wheel. Ordinary wheel at low velocity would look like that. Let's let it go by at high velocity and see what it looks like. So, that went by a little too fast. So let's slow it down so we can see what's going on. So still high speed, but we'll slow down the animation so we can see it. At high speeds, we begin to see Lorentz contraction, right? It's an oval shape, but look at the spokes. The spokes have the kind of shape that I was describing before because of the fact that the clocks in the front are lagging behind the clocks in the rear. Spoke first hits there, and then its other end hits the horizontal position, which means the spokes are bent. So that's a kind of cool idea. You can play around with that in a little animation, or I should say a little demonstration over here, where you can pick the velocity of the wheel. Now it's going the opposite direction, but it's the same idea. It doesn't matter. And you can pick the number of spokes that you like, all color-coded. So you can see this is a blue spoke, this is a green spoke, and they are all bent, and that effect becomes bigger and bigger and bigger. And if you had one going by at really high speed, the effect would be really significant. So this shows us an interesting example where asynchronous clocks show us that for an object in motion, it's not just Lorentz contraction that comes into play in terms of the distorting effects on the object. The asynchronous clocks come into play too and yield this unexpected feature of a bicycle wheel that the spokes will not be straight from our perspective.